Enzo. Okay, Enzo. Enzo, we are ready to start now. Enzo, Enzo. Enzo, we would like to start now.
Enzo, you are muted. Enzo.
Enzo, you are muted. We would like to start now.
Okay.
Okay, so let me introduce you. Okay, and then we will start. So welcome everybody. For those who are attending talk from La Trobe University, sorry for unusual time because we are running this seminar together with Probability Victoria seminar. And for Probability Victoria seminar, especially if we have international speakers, it's usual time. So this is my pleasure to introduce today's speaker, Professor Enzo Orsingher from Rome University La Sapienza. I know Enzo more than 20, maybe around 25 years, and always was interested in his research, his brilliant results, and diversity of his interests. So Enzo is now emeritus professor, but from his publications, you can see that he is still very active, working with many people, and I believe he produced a lot of very interesting and important results related to different areas, including random motion, random fields, different types of stochastic differential equations, in fractional calculus, fractional differential equations, and related areas. He is and was on editorial boards of several journals. He is a very active traveler, visited many countries as invited speaker, many universities, and in particular in Australia. At some stage, he was guest at La Trobe University, and I believe he gave seminars to several universities in Melbourne. And knowing Enzo personally, I just would like to tell that he is also very good in many areas which are not related directly to mathematics, for example, in languages, in running, and many other activities. So Enzo, you are very welcome, and now you can just start your talk, please.
Thank you very much for inviting me. And I want to say some words as an introduction to this field of mathematics, of probability. I have always been interested in working out stochastic models of random motions at finite velocity. It is very important to underline the fact that the type of motions in the plane were conceived to taking into account the inertia. That it means that differently from diffusion processes, in this case, in this particular models, the motion is performed at finite velocity. This is very important. And I restricted myself to the case of planar random motions, but some extensions in higher dimensions have already been done, also in non-Euclidean spaces. For example, in the Poincaré half plane or on the surface of spheres. But I think that it is more useful to take into account models which are intuitively explicit, such as those I'm going to describe to you. The classification of these planar random motions depend from a number of things. First of all, the possible directions. Motions can be in the plane with the minimal number of directions, that is 3 directions. The orthogonal case, where the directions are orthogonal, an arbitrary finite number of directions, and also, and this is very interesting, an infinite number of directions. So this is very important, the number of possible directions. The velocity, I said the velocity must be finite, and it can be constant, or it can be depending on the space, on the place where the particle moves, and it depends in some cases on the space and the time. That is, the velocity is a function of the place where the particle is moving and on the time where it happens to be located. Another important fact about these types of motion is when and how the directions are changed, which are the chance mechanisms which governs the changes of direction, the switches from one direction to the other. Usually, in order to obtain very explicit results, we assume that the process governing the changes of direction is a Poisson process. Homogeneous, and this is the simplest case, or non-homogeneous, where the rate of the Poisson process is a function of time. Another possible extension of this chance mechanism is to assume that the intertimes between changes of direction is an arbitrary non-exponential random variable. That is, a renewal process is governing the changes of direction. And in some cases, we assume that from each direction you can move to the neighboring directions with different probabilities. As it happens, for example, in a vortex, you have a different direction to move to the direction dj plus 1, that is moving counterclockwise or clockwise with a different probability. And you can move, and this is a more general case, you can move to all the remaining directions with, for example, an equal probability or a different probability. But the last case is too complicated, and I will not speak about this case. Look at what happens in this picture. I have drawn the set of possible directions at time t when the directions are orthogonal. You can move upwards or downwards to the right or to the left, and this means that you have 4 orthogonal directions. I have represented in this picture 3 different sample paths. For example, the green and the red sample paths, the particle moves inside the square. Instead, for the blue sample path, you arrive at time t on the border. That is, the particle moving in this form, in this way, can at time t be inside the square or on the edge of this square. And for this reason, you have a more complicated structure of the probability distribution. For example, I take the simplest case where from each direction you move to the orthogonal direction, upwards or downwards with equal probability, 1/2. This is the simplest case. And in this, within this framework, the possible set of positions at time t is the square, which is described in 1, or the edge, which is the set of delta s of t. In this figure, you have another possible set of directions. 3 directions are inside the square. 1 direction reaches at time t the border of this square. And it is important also to establish which is the amount of the probability of lying at time t on the border of the square. And this probability, you make these calculations, is equal to formula 2. You have an amount of the total probability on the edge and another part of the probability, which is inside the square. And there is also a moment in which the probability on the edge is exactly equal to the amount of probability inside the square. I call it the magic moment, and it is equal to formula 3. And you see that these magic moments, where there is a balance between the probability of lying on the edge of the square and inside the square, depends only on lambda, not on the velocity. And when lambda increases, this time decreases, because if the Poisson process governing the changes of direction is has a rate which is very big, the particle will continuously change the direction and will move inside. It will go away from the edge. In this third figure, you have the square, which extends as time passes, and you have some possible sample paths, some of which are on the border at time t, and some are inside the square, inside the square itself. The problem, a very important problem, is to determine the distribution at time t of the positions reached at time t of the moving particle. And the first result, obtained many years ago, is that the absolutely continuous part of the distribution solves a fourth order equation. This is a problem, because if you have 4 directions, 4 possible directions, the governing equation is of the order equal to the number of possible directions. This is a general rule. So you can produce equations of higher order with an arbitrary order, just moving from one direction, from one number of directions to another bigger number of directions. In this case, you have 4 directions. The equation governing the distribution of the absolutely continuous component of the distribution is equation 4, and has this 4. It can be simplified by means of this exponential transformation, and you pass from equation 4 to equation 5, which is still of 4th order, but you have inside here the Laplacian, you have the 4th order time derivative, you have this joint distribution, and thanks to this relatively simple form, you can find solutions of this 4th order equation. And the solutions have the form of products of Bessel functions, of derivative of Bessel functions, of products of derivative and Bessel functions. And this is the most difficult technical problem, to find possible directions possible solutions of that fourth order equation. You see, in mathematical physics, usually the heat equation, the wave equation, the Laplacian equation are second order partial differential equation. In this case, you must deal with higher order partial differential equations, for which it is more difficult to find explicit possible solutions. And thanks to this result, 6 and 7, it is possible in an explicit form to arrive to the distribution inside the square at time t in this way. Formula 8 represents the explicit expression of the distribution of the absolutely continuous part of the position of the particle at time t. You see, everywhere you have something depending on Bessel functions 9, which has this form. It's called Bessel functions of arbitrary imaginary argument, but it has simply this form. And thanks to this result, it is possible to arrive to the following fact. If you integrate the absolutely continuous part, you have exactly the part of the distribution which is not on the border. And this is the first important check. But what is more important is Formula 11. In Formula 11, you have a representation of the vector process representing the position at time t of the randomly moving particle. That is, you can express this vector in terms of independent one-dimensional Telegraph process UT, UT, and VT, which are independent Telegraph processes with rate lambda over 2 and c over 2. This is, from my point of view, the best result possible in this way. You have a representation of the vector process describing the moving particle in terms of one-dimensional independent Telegraph processes. That is, the distribution is 12, and since the distribution of u and v is expressed in terms of Bessel functions, it is not surprising that the joint distribution of the previous form is expressed in terms of products of Bessel functions. This result was first published in the year 2000. So far, I have described the planar motion with finite velocity c, where the changes of the directions are governed by a homogeneous Poisson process. What changes if the Poisson process is non-homogeneous? That is, the rate is a function of time. It changes, but not so much. Of course, it becomes more difficult, but it includes the previous model as a particular case. In particular, the probability of being on the border of the square depends, of course, on lambda. And you can have the following situation. If lambda is such that it integrates with integral, with finite integral, this formula is interesting. But if this integral is infinite, you have a completely different situation. In this case, it is possible also to have more detailed information on the behavior of the particle on the boundary. In particular, you can have a distribution of line on each side of the square forming the boundary. That is, you can explicitly work out the governing equation of the distribution 14, that is equation 15. This is the equation governing the distribution on each side of the boundary. This f must be, of course, non-negative, and we must integrate. This is important because it is on each side, while this formula is the overall weight of the probability lying on the boundary of the square. So if you solve this problem, you explicitly give the distribution for t lying in the point eta of the border of the boundary. And if you assume again that lambda t is constant, you have an explicit distribution, which looks like the distribution of the telegraph process, but this 4 shows that you have a different situation. The distribution on the boundary, the distribution inside the square of the vector representing the position of the moving particle is a solution of this 4th order equation, which is bigger than the former one, because lambda appears through also the derivative. You see, if lambda is constant, these terms disappear, and these terms disappear, and you recover the previous 4th order equation. This is a generalization. But what is very important is the following thought, that even if the governing the process governing the changes of direction is a non-homogeneous Poisson process, you have this representation. Of course, in this case, U and V are independent, one-dimensional telegraph processes, but in this case, the lambda is represented by lambda t over 2. So the velocity is c over 2, but the lambda is the rate divided by 2. But this representation is still valid also in the case where the governing process, Poisson process governing the changes of direction is a non-homogeneous Poisson process. This is, in a certain sense, the best result obtained in this work. Look, in interesting cases of lambda is, of course, lambda t equal to lambda constant. This lambda t lambda over 2, and you have the so-called Euler-Poisson-Darboux equation, which is very popular in hydrodynamics. Another case which is interesting is lambda of t, lambda hyperbolic tangent of lambda t, which was studied in a paper published in Statistics and Probability Letters in 2001 by Yakus. And the case lambda of t, which is lambda cotangent lambda of t. What is interesting is that in these two cases, Fong, Van Lock, Egarra, and Orsingher, all these formulas converge to infinite. So when you choose these rates functions, you have no probability on the boundary. You have only the absolutely continuous distribution inside the square. And this, in a certain sense, makes the treatment of the problem simpler, because you have not to investigate the two components, verify that one part and the other are complementary, and in a certain sense, it's simpler. This lambda t lambda over 2 and lambda t lambda cotangent of t, because initially you move and you change direction so rapidly that you never arrive at the border of the square. All this is summed up by the assumption that if this integral is infinite, no singular part of the distribution appears. That is, you have only the absolutely continuous part of the distribution. If reflection is possible, that is, you can move from each direction to the orthogonal ones, you have the description I have given so far, but if you can reflect backwards, you have a different situation, that is, the probability of lying on the border is different, and you arrive at this formula. So you must make some changes and you arrive at this result, if reflection is possible. Now, we consider another model. The model is that from each direction, you move to the neighboring ones with different probabilities. Velocity is constant, the rate is constant, but you have a vorticity effect. That is, you move in one direction or the other with different probabilities. And this introduces many changes. In particular, look at these pictures. You have two different situations. For example, here you have the possibility of reflection. In this case, you see, if you look at this sample path, in this point, you reflect backwards. So you run 2 times over a straight line. And the situation of the reflecting motion is a bit more complicated. And in particular, the probability of lying on the border, if reflection is assumed, leads to formula 25. Probability of lying on the border. Look, this is a complicated form. I remember that in order to arrive at this result, I quarreled for a lot of time with my co-author, but at the end we arrived at this formula: probability of lying on the border of the square when reflection is possible. And P and Q are arbitrary probabilities. P, for example, is the probability of moving counterclockwise, and P clockwise, and you have this fine formula. In particular, when Q is equal to 1 minus P, you have this particular case, and when P is equal to Q equal to 1/2, you obtain the first formula I have given to you, that is, you arrive at this simple expression of the weight of the probability of lying on the border of the square. This is also the distribution of being on the side, on each side of the square in explicit form. Making a lot of calculation, you arrive at formula 28, which gives you the probability of being at time t in the point eta of the square. That is, it's similar to the distribution of the Terrier process, but the lambda is different and is replaced by lambda times the square root of P and Q. In the case of random motion in the plane with reflection, you have also another singular component, which is the diagonals of the square. And the diagonal of this square, you have a positive probability because the lines capture the particle and they can move back and forth or upwards and downwards for the interval 0t. And this is the weight of the probability of lying on the diagonals of the square when reflection is admitted. If P plus Q is equal to 1, there is no reflection. You have still a positive probability, but it is located on the vertices of the square. the vertices of the square are at the same time on the edge of the square and on the diagonals, or the endpoints of the diagonals. So this is not surprising that you have this particular case. Now, I speak about something completely different, that is motion in the plane with infinite directions, which is, in a certain sense, simpler than the previous cases for a number of reasons, which I will explain. Look at this picture. You assume to be at time t equals 0 in the origin of the plane, and you choose initially the direction with a uniform law. You move along this direction chosen randomly up to the first Poisson event. Then you change the direction again with a uniform law, and you move so on. You can be at time t inside the square, inside the, not the square, inside the circle, and you can reach the circumference of radius ct if no Poisson event occurs, because you move along to the initially chosen direction up to time t, and you arrive somewhere on the circumference. Otherwise, if a Poisson event occurs, you will move towards the inner component of the circumference inside the circle, and you will be located somewhere within this set. So in the previous cases, you have 4 possible orthogonal directions, and the set of the positions is a square, which is expanding as time t passes. Here, with an infinite number of directions, the possible set of the possible positions of the particle is a circle, which expands with radius ct. You see here some details. At time t equals 0, you are in the origin. Then you choose a randomly oriented direction with a uniform law. If you assume a different law, for example, a law of the type E k cos of theta, becomes interesting, but it's very difficult because it assigns different distributions to the different directions, and you are not able to obtain explicit distributions of the position of the particle. Now, how to work out this model in order to obtain the explicit distributions? This C is missing here. This is a misprint. At time t, if we assume that the number of changes of directions is n, the possible position is represented by these expressions. You move along to the direction chosen, and the components of the position are represented by this expression. T are, of course, random variables. Theta is a random variable, and it is possible to obtain the explicit characteristic functions of this vector and invert the characteristic functions, obtaining a rather interesting and simple results. As I said before, the possible sets of the position of the particle is a circle, 31, and the boundary of this circle is a circumference of radius ct. Making a lot of calculations, it is possible to obtain the characteristic functions of the position at time t when the number of changes of direction is n. And you arrive at this formula where j of n is a Bessel functions, which is defined here, of arbitrary degree nu. And thanks to this result, it is possible to invert and obtain the conditional distribution of the position xt of y of t. Look, 34 is the explicit form of the Bessel functions. And when nt is equal to 0, as I said before, you are somewhere on the circle, making the border of the circle, and the characteristic function of the uniformly distributed law on the circle is j of 0. Important to calculate the characteristic function is this integral, 36, which is a convolution of two different Bessel functions. And I think that this formula is relatively simple, but it plays a fundamental role in order to obtain the characteristic function 33. And look, it is a gift of Bock to be able to obtain the distribution in such a simple form. If you invert the characteristic function, you arrive at formula 37, which represents the distribution of the particle at time t, conditional on the number of events and t equal to n. It is isotropic, that is circularly invariant, and depends on n in a rather simple way. And in particular, I draw your attention to formula 37. When nt is equal to 1, this gives this expression, which is related to the green function of the plane waves. There's exactly this form. And from the probabilistic point of view, it represents the distribution of the particle at time t when only one change of direction happens up to time t. When nt is equal to 2, this is extremely interesting. The distribution is uniform on the circle. It is incredible. That is, if you move in the plane with the assumptions I have introduced at time t, and you change 2 times the direction, you are distributed uniformly on the circle. If n is 3 or more than 3, the structure of this distribution changes because you have the maximal point in the center, and this maximal point increases as a sort of tower. Why? Because if you change many times the direction of motion, the particle has sample paths which cannot go too far away from the starting point. As it is at time t, you are somewhere around the starting point. For example, when n is equal to 3, you have this expression. While when n is equal to 1, most of the probability is around the boundary. And when n is greater than 3, the concentration of the probability increases around the starting point. By the way, in extensions to higher dimensional cases of motion, when the number of dimensions is 4, you have a similar expression for nt equal to 1. That is, if you move in the 4-dimensional space, you arrive at a uniformly distributed position at time t when one change of direction happens. When you are in the plane, you need 2 changes of direction to have the uniform distribution. If you want to obtain the non-conditional distribution of the position, you simply wait out the Poisson process and you arrive at this expression, which is the distribution at the time t of line in the point x, y, and it has a relatively simple form. Look, it's by far simpler than in the one-dimensional case where the distribution is expressed in terms of Bessel functions. And the cumulative distribution with respect to the radius has also a simple form. It is simple to evaluate the probability of being inside a circle of radius r with r less than c of t, and you have this type of expression. Now, the distribution inside the circle is 1 minus e minus lambda t. The magic moment in this case, where the distribution on the circumference and the inside are equal, happens at time t. I don't know how to call this symbol, and it depends on lambda. When lambda is increasing, this magic moment immediately appears. And another interesting fact is that the marginal distribution of each component is represented by this formula, and this is an integral expressed in terms of Struve functions. Another interesting fact is that the distribution of the moving particle satisfies the equation of damped waves. That is an equation which has this form and appears in the description, for example, of damped oscillations of a string. And it is possible to verify this fact by means of a series of steps. For example, if you make in this equation the exponential transformation, you reduce it to this form. By means of this important transformation, you arrive at the ordinary equation. Furthermore, this ordinary equation is simplified by another step, and you arrive at the proof that the general solution has this form. If you replace c with this expression and then you multiply by the exponential, you arrive exactly to prove that the distribution here is a solution of this equation. Now, another interesting case from the point of view of those who are interested in spatial functions is the minimal case. The minimal case is a motion in the plane where you have three possible directions. For example, look at this picture. You have three directions, rightward, this one, D1, or these two directions pointing to this point or this point here. And in the case of cyclic motions, that is, you are obliged at each Poisson event to pass from direction dj to direction dj plus 1 with this rule. You are you consider practically a motion where the particle winds up. You cannot move counterclockwise or clockwise in alternatively, but you are obliged to move only clockwise or underclockwise. In this case, counterclockwise. And in order to obtain some information from the probabilistic point of view, you must work on these probabilities. Probability of being at point x, y with direction dj, and it is simple to show that these probability functions satisfy this differential system with three unknown functions, which can be successively simplified by means of this transformation, becomes 52, and this important transformation, this system becomes the system 54, and in order to work out the explicit distribution, you must transform this partial differential equation into an ordinary equation, and this ordinary equation is the third order Bessel function. Note that we are moving with a minimum number of directions, that is in the plane 3 directions. You are moving with a cyclic type of motions, that is, you are obliged to move subsequently from direction dj to direction dj plus 1. And you arrive at this expression. This expression can be written also in the form of 57. This is a generalization of the Bessel operator. This is a third order Bessel operator. And the solutions of this third order equation is like this. And this is a class of extensions of Bessel functions. We depend on two parameters, m, n, and of course 3. Look, for example, when k is, when m and n are equal to 0, you have 3 instead of 2. 3 here instead of 2, and you have k factorial to the power 3 instead of 2 to the power 3. That is an extension. What is very interesting is that you produce a rather relatively simple type of random motion where Bessel functions of third order appear. If you extend this to higher order, that is, you move in the minimal, with a minimal number of directions in the Euclidean space of dimension d, you have a similar thing, of course, much more complicated because it involves Bessel functions with a number of parameters depending on the number of dimensions. Okay. After all this, it is possible to obtain the explicit distributions in terms of Bessel functions. And these formulas 60, 61 are conditional distribution on the number of changes of direction. And then you can put them together, weighting out with the distribution of the Bessel function. Most of the results I presented, most of the results are published in the paper appearing in 2033. But if you want to obtain particular cases, you must look at the references inside this paper. The last part, minimal motion in the plane, is treated in 2002. And previous results are published in papers appeared in the 19 years. This is all. I think that I used all the time you gave me.
Okay, thank you, Enzo, for very detailed talk. And now we have time for questions. Just unmute yourself and just ask questions.
Mm-hmm.
So I have a question, Enzo. This extraordinary uniform distribution after 2 changes of direction, do you have any intuitions for why that should be?
This motion.
No, I think it was the orthogonal motion.
The orthogonal.
Yes. two changes of direction, and then you had a uniform distribution over the
Yes.
interior. That's sort of most beautiful result. Is there intuition as to why that should happen?
This formula 11, where in the orthogonal motion you have
Sorry,
the
Enzo.
position, the
Scusa,
vector.
Enzo. I think he means the other model, where you have.
Sorry.
I think it's the other model. You mentioned that if you have two changes of directions, there is a uniform over the sphere. It was in the later slide, I think.
That's right. You're right.
It is.
Keep going. Keep going. Keep going. It's this model, but it comes later.
Later.
Nelle slide dopo. Questa qui. La slide di prima. This one.
But there we are, yes. So the special case with the uniform distribution.
This one.
Yes. Sort of magical result.
It is an incredible result.
But he's asking about intuition. If you can explain, if you have any heuristics behind intuition.
The heuristic, you know, I was so doubtful about this result that I tried to make some, how do you say, simulations, taking many sample paths when the number of changes of direction is 2. And in effect, the endpoints of these sample paths look as they were spread uniformly on the circumference. So why? I think that an intuitive explanation is the following one. Look, when nt is equal to 1, this distribution means that you have a big probability around the circumference, because when x is equal to c of t, this is 0, this becomes infinite, and you have big probability, because when you change the direction at least 1, you move inside the circumference. If n is equal to 3, that is, you change 3 times the direction, you have sufficient time to return back to the starting point. In the middle situation, where you change 2 times, you are certainly far away from the circumference, sufficiently away from the starting point, so you have an intermediate situation, because in this case you move outside, but at the same time you have the time to go back. But mathematics shows that it is uniformly distributed. And I told you that in the extension of this model to higher dimensions, in the case of 4-dimensional space, this uniform distributions appears when you change once. Why? I don't know. In the 4th-dimensional space, if you change direction only 1, you have a uniformly distributed vector inside a sphere of radius ct.
It's just in dimension 4 or any other higher dimension?
No. In dimension 3 or 5, it doesn't happen.
Okay.
It doesn't happen. I don't know why. I have a lot of collaborators who worked with me, and the only way to convince that this happens is to make simulations. But an intuitive explanation is this one. Imagine that when you change direction once, you have a push outwards towards the circumference. And this means that you have a big probability in the neighborhood of the circumference. When you change 3 times, you have a concentration of the sample paths around the starting point. In the intermediate situation, you have the uniform law, not so far away, not so close to the starting point, you have a uniform distribution.
Okay, thank you. Any other questions or comments? Answer, I have naive and maybe very distantly related question. So what you did, you look at motion and then you obtain distribution on the boundary in many cases. So say if I know distribution on the boundary, so I don't know, of course, what is NT and all other things. Can I somehow find or infer something about my motion?
If you know the distribution, the weight of the distribution of the boundary, you have only the information that the remaining part of the distribution is inside. But how it is distributed inside, it is impossible to guess it from the knowledge of the distribution of the boundary. It is important. You can only say this: near the boundary, the distribution of the absolutely continuous distribution must be similar to the distribution of the boundary. And this is really what happens. But you cannot say which is the explicit analytical form of the distribution. You can check that near the boundary and on the boundary, the distribution is similar.
Mm-hmm. So you can, or somebody can construct, say, two motions with exactly the same distribution on the boundary, but which are in some way not equivalent. Yeah, not similar.
Yes, but in this case, the rules of the motion must be different.
Mm-hmm.
But you can imagine, yes, fix the distribution of the boundary, and inside with some other rules, you have a different behavior of the moving particle.
Okay, thank you. Okay, any other questions or comments? So if not, let us thank Enzo again. And thank you for your time. Despite all other difficult things that you told me, that you found time and joined us and gave this talk. And so next seminar will be in 2 weeks. Yeah. So
thank you very much. I am very happy to see you after many years. I don't remember when it was the last time we met in Kiev. Maybe it was 2012.
Yeah, but you visited Australia in 2017, I believe.
But I remember Kostya, we met in the university and in Moscow. Maybe you remember that we passed some times in the Sheremetyevo airport.
And so we actually met in Leningrad as well, which is known as St. Petersburg again.
Yes, also
Yes.
in
I think it was maybe
St. Petersburg, yes,
It was
but in many places. But you came also to my office in
yes,
Rome.
yes, yes. I remember.
I remember about the details of that striscia. And Andrea, I met Andrea for the last time in 2014 when I visited Melbourne.
Yes, we had a very nice trip. It was very nice.
Yes, you showed me Koala and the Great Ocean Road. Yes, we often, with my wife, recall that trip and recall you and your French friend.
Yeah, Gabriel. He was visiting as well.
Yes.
All times nice.
Okay.
Very
Thank
nice
you
to
very
see you,
much for your
Enzo.
attention.
Thank you.
Ciao.
Stay safe and
Ciao.
healthy.
Bye.
Bye.
Goodbye.
Bye-bye.
Bye, everybody.